Now switching the wavelengths by several orders of magnitude to the shorter side. Maybe it should have been the opposite, but we go backwards now to the shorter side. I'm talking about optical remote sensing of snow and ice, more or less giving, because there will be other lectures on these products, snow products and snow extent and physical properties. I will rather focus here on radiometric properties, physical background like refractive index and so on, and then also quite some information on atmospheric radiative transfer and corrections for atmospheric propagation. Actually, this was the topic where I made my thesis. My thesis work starting in the, shouldn't say, late 1960s, was on atmospheric radiative transfer for numerical methods already. This was with numerical methods. I started computing with SUSE and then switched over to CDC 3300. SUSE was one of the very old computers with, I don't know, very historic. Anyway, so, and then did work in version of spectral measurements in the radiometric measurements to invert for aerosol and the water vapor and so, and pollution in the atmosphere. So this was my thesis work, and then I switched over to remote sensing, which was not a bad start to have this start come from this field. Now, in the lecture, as I mentioned before, I start with these radiometric issues. What we will hear about here is mainly the parameters we're looking is irradiance, which is the radiation on an area increment from the semi-space, so like here from all around or outside from the heavens. And then this is one parameter, and the other one is radiance or spectral radiance, which is directed into radiation directed into a narrow beam. The basic is for the processes going on in the radiative transfer equation, which is the change of radiance along a path which has loss terms for absorption, like, for example, gases in the atmosphere, water vapor, and so on, and scattering, which means that radiation scattered out of the beam in other directions, and then source terms, which on one hand is the black body radiation, which depends on the temperature and the emissivity of the constituent, and on the other hand, source term for scattering, and this is complex, and this really causes other problems for correcting atmospheric effects, because it depends on, of course, on the scattering property of the medium, but very much on the incoming radiation, which depends on this so-called phase function from all around. And this phase function is the integral of the whole space of the phase function is 1, which means it just describes the distribution of the radiation in the different directions. And this can be very different for different types of aerosols in the atmosphere, but also, of course, if you go into the snow, for different snow grains and snow structures. Now, the refractive index of ice in the visible and infrared medium is this shows the real part and the imaginary part. The square root of the refractive index is identical to the permittivity. And to the relative permittivity. And we can see here that it's up to wavelength of 2 micrometer, there's not much change, then it drops, which is, and then it stays about 0.35. So this change is related to a large loss in the 2.8 micrometer absorption band, and from there on we have this very big change, many orders of magnitude, from 0.5 micrometer, 500 nanometer, to 2.8 micrometer in the absorption, in the imaginary part. We heard before about this penetration depth in an absorbing non-scattering medium. This really doesn't have a significant role in snow because penetration, it penetrates several centimeters maybe in snow, the visible radiation, but and it has a little bit an effect also on the thermal structure, but it's really marginal. It's really a skin layer which is affected. But it would have in ice, for example, but also only if it's the scattering, even in glacier ice and so, scattering is quite efficient. And so this penetration is not an issue which you would use remote sensing for studying, but of course it's clear that in ice you can get quite some significant penetration, but as I mentioned, this equation with only absorption, this is not useful because scattering losses are more important. Now, the spectral reflectivity of snow is largely affected by grain size, and in particular in the visible, it's not so much, but if you go to the near infrared, and this is a model computations, and here you can see that it's this is of course extreme case. It's from ranges from 1 millimeter to 0.05 millimeter, but it indicates these model computations with an incidence angle or of zenith angle of 60 degrees. It's very significant. And this is then used for computing grain size. Whatever, I mean, grain size is also not, it's a bit, in my view, not a very well-defined parameter because grains are not, I can have quite complex shapes, so it's a parameterization. Then what's important, there is soot has an important impact, and that is a model computation, and also for different grains, 0.1 millimeter and 1 millimeter. And in these both model computations, the size of the ice grains is largely different, but the soot content is the same. So the imaginary part is 0.5 in both cases, and also the radius of these particles. And you can see that in case of soot, we have here, for example, in the green wavelengths, 0.7 reflectivity with 10 parts per million of volume, and here we have only 0.4. I should mention, with this model computation, it depends very much where you put these soot grains, but here they are included within the ice grains. If you put them outside, then it looks different. So this is just an indication how it works, but it's not. It can be quite variable. This shows the refractive index and albedo of polluted snow. And this example, it's also model computation. This is the imaginary part of refractive index of a snow soot composition. And for carbon particles. And carbon has a very large imaginary part. 0.5 is quite large. This is a real part, 1.8 of the imaginary part, so very large losses. And already a low volume fraction of soot, here for example, 1 times 10 to minus 6 has quite a significant change in the losses. And here we have model computations and compared with measurements. And we can see here it's a rather fine-grained snow in the model computation. Assumed it was dry snow to match. These numbers were used to match approximately the observations. And you can see here that we have here, of course, again, this drop in the near-infrared, which is confirmed. And in the visible, there's not so much difference in these cases. And it's the soot content is rather low, 2 times 10 to minus 8, and here we have slightly higher numbers. Here it is increased, but not very significant still. So it was not, I wouldn't call this a real polluted snow. Now, if we go to measurement, it can look quite different. This is an example from impact of pollution on spectral reflectivity based on field measurements of spectral reflectance. They were made with a VIS, the Airborne Visible Infrared Airborne Spectrometer of NASA JPL, which has 224 channels. And it shows on one hand dirty snow in the San Juan Mountains. These mountains are in the western Colorado, very close to the dry zones and deserts of Utah. And the source of the dust there are these dry areas of the Colorado Plateau. This is one. And these dots are the theoretical curves for 0.5 and 1 millimeter grains, these dotted curves. Then for clean measured snow, it's this full line here. We see also the drop. And looking for this dirty measured snow with this dust. This measurement was made in high winter, and this later in spring. And then we can see a large increase, actually, from blue and green to the red wavelengths, and then again a drop. Similar story, the snow with red algae in Sierra Nevada. In German, das heißt das Blutalgen, these are red algae, and we sometimes have it on snow. And then here, of course, what would you expect? A peak of reflectivity in the red wavelengths, red visible wavelengths, and still quite high in the near infrared. So we can see if it's polluted, it can be quite variable. Now, this is an example which we, Gabriele will give you a practical course actually on snow wetness, but nevertheless they did this analysis on Argentière Glacier. And this shows a similar behavior. It's late summer albedo of snow and ice on glaciers. And these are Sentinel-2A data, but it's reflectivity. This is based on the top of atmosphere reflectance data of Sentinel-2, but they were atmospheric and topographically corrected using the 6S radiative transfer model somewhere in late August 2015. So it's surface reflectors, and we were interested in the differences of reflectivity in the different glacier zones. And for this course, there were also Pleiades data, high resolution optical data available to check for the different glacier phasis zones. And this is this yellow line. So we had here in the uppermost part snow from the last winter, not much left, which we can see. And then we have here, actually it goes down, we have down here ice, and this dark part, or low reflectivity part, this is firn. Firn is largely polluted snow from previous years. Firn and ice would be an area which belongs to the negative surface mass balance, which means that mass during that year is lost. This is depletion of mass which has been available at the beginning of summer but then melts away. And positive mass, ice mass, gain in mass would be in this area of snow, this upper area, which partly would be in the shaded area. And all this was corrected. Also the shadowed zone was corrected, therefore this appears here so bright. It's interesting. This is the uppermost zone, and as I mentioned before, we had this topographic correction for irradiance. We used the different spectral irradiance for shadowed zone and solar illuminated zones, and then we get this albedo map, and this is really here quite bright, appears quite bright. This is in the shadowed zone, and here this is snow, and then there's a transition to firn, and this transition between snow and firn is not always very clear. I think we will hear more about that with Frank, how difficult this problem is, because it would be interesting to know exactly the line where we have a gain in mass in the snow area during the mass balance year, to the end of summer, and we have a loss. And firn, where firn melts away, this is a negative part. So quite tricky. Now, another issue which calls very much, why do we use satellite data? And this is that we have a large spatial and temporal variability of albedo on glaciers. And this is a very nice example, which Hans Oerlemans, who shows albedo measurements from May till early September on field sites on Vatnajökull in Iceland. Showing here the location of these sites. There's one on the terminus of Breiðamerjökull, and we can see here that there's a gradual decrease of albedo during summer, which is quite continuous, which means that there may have been a little bit of snow there, but it's essentially linked to glacier ice. which gets more polluted. Then we go a little bit higher up on Biedermeierkettel, and there we see a high albedo till early June, and then it drops. And it drops to values of 0.1, 10% reflectivity. And that's not so obvious here, but what can this be? You can see on Skyrayerkettel that this is very likely an ash zone. So ash, these are ash zones from volcano outbreak which come out, and there you have throughout summer very low reflectivity. Then we come up to 1500 meters. Here it fluctuates around between 0.75 and 0.95. These peaks are snowfalls during summer. And then this is a zone a little bit lower, 1200 meters. Here again the winter snow, a snowfall, decreases again. And then here we drop down to ice, and also there must be an ash zone coming out here. And then a peak of first snow in between. So very clear, if we want to get the surface mass balance of this glacier and the energy balance of this glacier, the fluxes, we need satellite images and good time series. Now, for deriving the albedo, there's one problem is the angular dependence of snow reflectivity. This shows results from measurements which were made. I think it was made on Col del Port near Grenoble, and it's the snow surface is melt freeze crust, and at different incidence angles. And we see that solar incidence angles. No, not solar incidence. It's the incidence angles of the spectrometer. And here we have vertical, and then we go up to 60 degrees. And 60 degrees, we have a little bit of specular component adds, and we get higher reflectivity than if we would look vertical down with a spectrometer. And this is throughout all the wavelengths here. And these plots are hemispherical directional reflectance factors, which is the irradiance from the in the view direction of the sensor, divided by the irradiance from the sphere, half sphere, which is given by the diffuse and the direct irradiance. And here we assume a direct solar irradiance, for example, or whatever the source is. Here we assume in these examples 30 degree theta s, and the forward direction is the azimuth angle 0. Okay, this is forward direction, that's different wavelengths, visible 0.55, 0.85, that's already starting with the near infrared and going on to the shortwave infrared. All these examples show the highest reflectivity in specular direction. This is relative to the total, higher than the average, and lowest in the other direction, and then it is distributed in other azimuth directions. And but this is given at all wavelengths, but in principle the relative change is largest in the near infrared. For example, here we have a difference between backward and forward, which is a factor 2 times. It's 2 times higher here, and here it's maybe it's 15% higher only. But this is also evident here, that the relative change, the relative angular change is larger in the near infrared than in the visible, which plays then a role if you want to compute the total albedo out of this of directional data, the total reflectivity which you need for surface radiation balance computations. Now, very briefly to the near-infrared emissivity, this is actually also an issue which is important because it refers to the computation of the temperature of the surface, whatever, even for meteorological models, for climate models, and so on. And also this is not one. You cannot assume that the emissivity with snow is 1.0. This shows here the emissivity between 1 and 15 micrometers. I just show the atmospheric window is really where we do most temperature measurement is between 8.5 and 12 micrometer, which absorption band of ozone, O3 in between. But so it's maybe mainly this range for temperature measurements on the surface, but also here it's not close to 1. And these are really measurements in this publication by Painter and Dozier shown. These were measurements of emissivity in the Sierra Nevada, and it shows for one case quite high values up to 11 micrometers, and then this drop. And in the other case, there's lower values starting at 3 micrometer and then a maximum at 11. And these are the related brightness temperatures, the difference of brightness temperatures minus actual thermodynamic temperatures. And the arrow here would be, for example, almost 1 degree, and here would be 1.8 degrees. In this case, here it's still, maybe still on the order of 0.5 degrees. These different curves, they don't write exactly about the viewing angle, and they mention it's near nadir, but a little bit difference in the viewing angle makes a large difference in the emissivity. And this is shown by these curves here. Model computations in a recent publication by Nully. And you see here between 3 and this goes up to 50 micrometers, where you see emissivities at incidence angle between vertical and 75 degrees. And also in these, for example, here you see differences ranging from 0.985 to almost close to 1. And at 0, it's much less difference. But also at 9 micrometer, in that part of the window, we have already significant differences. This is a model computation, and this other example shows something which is used now. For example, in the numerical meteorological models, also climate models. This is a spectrum, so-called community radiative transfer model, snow surface emissivity spectra, used by NOAA and Estes in their models. And they assume this is wave numbers here, so we start here 10 micrometer and here 3.3 micrometer. And they show, they use in the atmospheric window for both old snow and fresh snow the same numbers, about 0.99, which is quite different from that. And then it drops at shorter wavelengths. And this is really it may look insignificant, but it's not, because if you go to the global scale, it makes a difference in the energy balance and energy transfer. And now with this CRTM, they're now considering maybe they need to have to take into account the incidence angle maybe, and maybe they should check the model. So this was the reason for these recent publications by Nali et al. Now, going on to atmospheric radiative transfer. This shows the irradiance on top of the atmosphere. This is for the standard atmosphere computation, which I made for the standard atmosphere. In spectral irradiance, watt per meter square and micrometer. This is radiation from the half space with vertical solar incidence. And you can see the difference. Diffuse radiation is higher, of course, in the visible wavelengths. You have the absorption bands. Ozone is important at short wavelengths, and also still in the visible. Then you start with different absorption bands. It gets more important, of course, in the near infrared. And this are the wavelengths which, for example, the sensor like Sentinel-2 MSI use, for example, to compute the water vapor. But for the surface, you avoid, of course, for measuring surface data reflectivity, you avoid this band. And this is the radiance emitted from a surface, in this case, without atmosphere, with the atmospheric contribution. And these are the black body curves, and you can see again here the atmospheric window. There are also absorption lines within this so-called atmospheric window. This is ozone, and for temperature measurements you use mostly this range between 9 and 12 and micrometer, or even usually there are several channels in this window that you can correct for these absorption losses. Now, for computing the surface reflectance, first order radiative transfer model shows that we have on one hand the surface reflectance, which has irradiation from direct radiance and directly from the sun, and diffuse, which comes from the half space. And then we have reflected radiance directly and diffuse, multiple scattering to the sensor. These are the main three components. And this is an equation for the surface components. It's, as I mentioned, it's the irradiance, and then you have the losses of the radiance exponents of the atmospheric optical thickness. And then we need to estimate the radiance of the atmosphere, the scattering within the atmosphere, and the reflected radiance of the adjacent area. The surroundings is quite important also. This shows an example of top of atmosphere radiance. We made measurements and campaigns with MARIS, the spectrometer on ASAR, on Envisat, and these were the measurements in the 15 channels on 19 February and then 15 January. And computing the surface radiance, we applied the 6S atmospheric correction model, and we get here, with these inverted numbers, very little difference, spectral variability, even a slight increase. One was in the lower curve was in April, which can happen, because snow was polluted, and another one with MARIS, and the other one was in January. The field measurements were also here quite low in April, wet snow. I have some doubt about these high values in the field spec. I think we somewhere came close to specular with the angle. The solar angle was very low, so we had the impact of the... So in this case, I think these inverted Maris data are not so wrong. So that's... Now, I talked about this 6S model, which is a parameterization of the full atmospheric correction model. There, in the full formulation, the top of atmospheric radiance is the incoming radiance from the satellite, from the surface, times attenuated through the transmission through the atmosphere. So this is a reflected radiance at the surface. And this is now the path radiance, which the radiance which comes from the atmosphere, where we have on one hand from the surroundings, adjacent surroundings, and one hand from the direct and diffuse radiation. And this is quite complex. We need the phase function, scattering function, phase function, which is a distribution of the radiation, in which direction the error will scatter. And this then needs to compute it numerically in many different layers. We need to know estimates for the phase function. So this cannot really be solved well. And there are some parameterizations, like this tool, computer tool, which is available, publicly available computer code for 6S, second simulation of the satellite signal in the solar spectrum for calculating the downlooking planetary albedo, which then can be inverted for the surface, for the reflectivity of the surface. So we have, on one hand, the reflectivity in the atmosphere for aerosol, and this is atmospheric reflectance, these two components, this and this one, and then the signal from the surface attenuated on the path through the surface, and then the incoming direct radiation and the incoming diffuse radiation, and there is a parameter which represents the spherical albedo of the atmosphere. So what we need is really, we need an estimate of the albedo of the surrounding area to invert this, and we need an information on this scattering function of the atmosphere. And this model, you have a choice of atmospheric aerosol types. It's computed in different atmospheric layers and so on. But it's quite tricky to get these numbers, and you can do this iteratively. But of course, it's still not perfect. So with all these estimates and corrections for at-surface reflection, in particular if the topography comes in, it's quite tricky. I show here examples for these phase functions. These are different types of aerosols. For example, here on one hand, they have on one hand different absorption. Scattering phase function is the ratio of reflected over absorbed versus total scattering, and here we have very little absorption, and here carbon particles we have very large absorption. So the scattering function, scattering amounts to 25 to 30% of the total losses. And here the scattering amounts to 1% of the total losses, scattering losses. So this is, of course, also one problem. And then the directional dependence depends very much on the size function of the particle. And of course, you can use, when you try to estimate the scattering function in atmosphere, you can assume for certain regional parameters, certain assumptions. If you go to higher altitude, it's also better. So still in the cryosphere, still a little bit off than for other applications. But the point is we have quite different angular dependence. This is a typical example on the angular dependence of backscattering contribution now for vertical solar, for vertical transmissivity compared to aerosol. And aerosol gets in percentage more important when you come from the visible toward the near infrared. Another difficult problem is the solar illumination and reflectance in a complex terrain. This shows the different components or contributions. This would be direct and diffuse irradiation on a horizontal surface, and this in the mountain. The irradiance. So the direct solar, here you can run into shadowed zones. And this is a diffuse, in this case, for example, much smaller part. Now these adjacent terrain effects, in the flat area, none. Slope reflected also. The reflection is given by the incidence on the horizontal surface. And the adjacent terrain can be very different. Slope reflected radiance, for example, here, and can play a significant role even in the shadowed zone. It's not shown here, but for illuminating this shadow. It's not only the diffuse irradiance in this zone, but you get also reflection from the opposite slopes. Yeah, it's shown here. And this is also illustrated here, where you have the atmospheric path radiance. This is direct. This is the reflected radiance, which we are mainly interested. Then there's the background from opposite slopes. We have the diffuse and mantle. So it's not so easy. And this is an example how this may look like. These are the sentinel channels. This is a false color representation of the channel 11 at 1.7 micrometer, then 8 at 950 micrometer, and channel 4 at 750, 700 micrometer. And this is a shadowed zone. This is an image MSI of site near Grenoble, and now it's near Chamonix. And I will show data along this of these points, the spectral curves. This is a shadowed zone. You can see here snow in the shadow. There's snow in the sun. And there is snow-free areas. And there's again a little bit of snow. And these purple points are snow-covered, and these green points are snow-free, either in the shadowed zones or in the sun. The dots are in the sun. And we developed a method which is called multispectral unmixing with locally adaptive endmember selection, to account for the different spectral irradiance in shadowed zones, because in shadowed zones we have much more blue components and short wavelength component in the diffuse radiation than in direct solar radiance. And we're using local selection of end members. Spectral decomposition uses spectral reflectivity for specific targets. And here we separate snow-free and fully snow-covered and use this data directly from the images, always automatically. This is important. And we provide also error estimates for this. And this is not only done for MSI, also for other sensors, Sentinel-3 sensors, for example. And this shows now the difference between these curves. For example, in this case, this is in the zone which are illuminated by direct solar radiation. And here we have the green dots are snow-free. These are apparently vegetated areas, and this where the vegetation is not active, and this is in lower region where we still have quite active vegetation, or maybe it could be also coniferous forests, and this may be grassland. And this is snow. And we have the high, this is top of atmosphere reflectance, by the way, not atmospherically corrected. And we have high reflectivity in the visible, and also up to about 900 micrometers almost. And then high reflectivity at 1600 nanometers in the snow-free, where the vegetated areas are. And this is now in the shadowed zone. And there it's very different. These top of atmospheric reflectors are not corrected for this topography, but also the spectral behavior is quite different. We have quite low reflectivity everywhere in the above almost all the near-infrared and mid-infrared. It drops very much from this region where we have the diffuse irradiance, blue and green area. And this means that we cannot do appropriate spectral unmixing without separating these areas. And this is shown here, for example. This is now the reflectivity on the left side with the normalized different snow index, which is visible reflectivity minus shortwave reflectivity, shortwave infrared reflectivity divided over the sum of these. And there, because we have this quasi-zero reflectivity in the shortwave infrared, which in this case, let's go back here, it's in this region here, where we have still quite some reflectance. So if we use these same end members, we get, this is snow-free actually, we've seen, then we get here full snow cover. This is a fractional snow cover, and this is now with the other method where this is well discriminated and separated. Now, just finally, I will briefly address another issue which also makes it quite difficult. This is going to vegetated areas. If the forest is too dense, then you get snow if there's snow also on the trees. That's a so-called viewable fractional snow cover. Fractional snow cover means percentage of snow cover within a window of the whatever window size you use within an image. And if you have a forest, of course, like the open forest here, then it depends very much how much snow you are seeing. This is from vertical, and here you have a Furgal gap fraction, which means you see the snow 74%, and here it's oblique. You have an angle of 55 degrees, and here you see only 37%. Again, you cannot use the same parameters to retrieve this snow cover. And this is an example using the MODIS snow-covered area and grain size products. And they provide fractional snow cover and grain size. And they apply this, again, this multispectral unmixing model. But they use spectral mixtures and member mixtures from a library of snow, vegetation, rock, and soil, which means they do not yet, maybe they do not yet, I hope they will later discriminate the shadow and non-shadow. But of course, then you need to use digital elevation models and so on, so it's quite tricky. And this example shows now here this viewable fractional snow cover. And this is now adjusted for this vegetation fraction using also this fractional snow cover, accounting also for the incidence angle. And this makes really a difference. And this is this vegetation factor. Okay. Now, this is references, and with this example, I raised some issues and questions. I'm sure that you will have lectures on this in the next days, and they certainly will give you more information on this snow extent retrieval and also on the inversions on optical parameters of snow like grain size and albedo. Thank you for your attention. Questions, please?
You showed this example of the ash zones on the glacier, and I wondered, did someone quantify how much faster the glacier melts in these areas where later was removed?
Yes, the colleagues in Iceland did a lot of work on this because it's really significant. Yes.
Do you know, like, some percentage of how?
Yeah, I don't know. So, yeah. But an albedo of 0.1 on a glacier is dramatic. Yeah.
Maybe as a very short comment on this, when this ash layer has a certain thickness, so let's say a little bit more than 2 millimeters, it is a strong isolator. So it does not melt in, but prevents.
Yeah, but I think it must be thicker because it gets heated.
Yeah, but not much because there's so much air between. So it's really a very good isolator.
Could be, yeah. Yeah, maybe, yeah.
It depends on what kind of ash it's for.
Yeah, but this is very absorbing.
Yeah, of course. But just for the...
Yeah, okay, yeah. I know that debris has a strong impact, but these are usually thicker, like on the Himalayan glaciers, also on our glaciers a little, where you have debris cover, but otherwise you have, for example, in the cryogranite holes, a little bit of ash and dust, then it accelerates the melting. Okay, interesting, thanks.
Can I ask about this last slide? What happens if you have snow on the canopy?
This is classified as snow cover. snow cover. This is a so-called viewable snow. There are products called viewable snow, and I'm sure they will hear this will be given details in these lectures, but there are products called so-called viewable snow, and then you can, sometimes they also extrapolate from the viewable and assume that in the forests beneath or besides, it's the same.
So in the Moscow product, they have libraries, right?
They have the spectral library, yeah.
But in the product you showed us the Lamsu.
No, we take it in the Lamsu, which was developed at NBO, we take it from the images.
Okay, so you have some sort of classification of...
Yeah. But this has been published, but it's still not in the operational way. For the operational use globally, daily, it's of course a bit tricky, and we need to find out how to implement this. It's still an open issue. We do it for regional products, high-resolution products applied. But for the global, it's still wonder how to go ahead with this. Okay, I think the next lecture.
Okay. Thank you. Okay, so now we will pass to the two first exercises. And the rooms for exercises are upstairs, so when you go out from the room, you go on the stairs and then you go towards left. There is like a sort of aquarium, like everything is glass. And now, wait just a second. One information, very important. So we are 48, and in each room we have 20 computers. So in practice, we need 4 couples in each room. So I don't know if you are maybe want to be together. Okay, we have 1 volunteer couple. So I mean, you don't have to stay like this for all week, no? Maybe then you can change tomorrow. Then we have also some other computers that are outside of the computer room. So in case it is not very comfortable for you to be as a couple using one computer, maybe in the next exercises you can also, if you feel comfortable, you can take the file with the tutorial, let's say, how to proceed with the exercise, and maybe you can do it and then talk with the teacher, no? It depends how you want to do. But in general, we need 4 couples like that. So be prepared. And let's see each other upstairs.